Hello everyone. In this video we're going to start Unit 4-3. I suspect we'll get through the first couple of pages in this video, and then we'll finish up the section in the next video. So what we're going to learn about in this section is how to use the Laplace transform to help us solve slightly more complicated differential equations than what we saw previously. So let's go ahead and get started. I encourage you to read all of this stuff, the overview and the introduction. Okay, so here we have our differential equation, y double prime plus 3y prime plus 2y equals 20e to the 3t. And we have initial conditions, y of 0 is 0 and y prime of 0 is 7. So what we're going to do is apply the Laplace transform to find the equivalent algebraic equation. Okay, so here we see on the left-hand side, we take the Laplace transform of y double prime, which is s squared y, capital Y of s, minus s times little y of 0 minus little y prime of 0. We take the Laplace transform of 3y prime, which is 3 times quantity s capital Y of s minus little y of 0. And then twice the Laplace transform of y is just 2 times capital Y of s. And on the right-hand side, we'll get the following. And this identity can be found by looking at one of the charts from the previous units. All right, so we're going to get an algebraic equation out of this. So let's combine some like terms here. You notice we have s squared times y of s. We have 3s times y of s and 2 times y of s. So really what we have is s squared plus 3s plus 2, all of that in parentheses times capital Y of s. We know that little y of 0 is 0 and little y prime of 0 is 7. So y of 0 is 0, that much is gone, that much is gone. And so we get minus y prime of 0, which is 7. And everything else is already captured over here. All right, so this is our algebraic equation then, right? And so we're going to come down here and now just solve it to show that we get this expression here. Well, what I'm going to do is add 7. And then divide everything by s squared plus 3s plus 2. And this s squared plus 3s plus 2 divides into both parts of the numerator, so it'll add an extra factor of s squared plus 3s plus 2 in the denominator of this one, and you'll just get 7 over that. So you get 20 over s minus 3, s squared plus 3s plus 2, plus 7 over s squared plus 3s plus 2. Ta-da! All right, so that was an easy first page. Let's turn to the second page of Unit 4.3, where we see now that the answer that we're looking for is, well, we solved for capital Y of s, right? That's what I should have written here. However, if you look on your chart, there is no identity for something like this, right? So that's what number 3 is asking. Like, can we find these expressions in the table? If not, which are closest? Well, if you look back at your tables, so look back in your previous units, we know what to do when there's a constant divided by like s minus some number. However, it doesn't allow for extra factors in the denominator, right? Like, so something like this, it maybe looks like there's a 20 over e to the 3t, but that's really not what's going on because you have this extra factor in the denominator. So not really, I guess, is the answer here. Can we use the table? Not really, but we see that if we're able to separate the denominator according to its factors, then maybe we're getting somewhere. Well, if you remember, that's going to be the idea from Calc 2 of partial fraction decomposition. Okay, so what we're going to do first is recombine 20 over s minus 3 s squared plus 3s plus 2 plus 7 over s squared plus 3s plus 2. We're going to rewrite all of this as one single fraction. So you'll notice the common denominator is s minus 3 s squared plus 3s plus 2. The key observation here is that the 7 already has this factor of s squared plus 3s plus 2, so it just needs an s minus 3, whereas the 20 doesn't need anything, right? And you simplify this, you notice you get 7s, that's the 7 there. You get 7s minus 21 plus 20, so I think this is going to be 7s minus 1 over s minus 3, s squared plus 3s plus 2. All right. Now, there's one last thing we're going to do before we proceed, and we're going to take this and now totally factor the denominator if possible. And you'll notice that this s squared plus 3s plus 2 actually does factor, and we're only going to try to factor over the real numbers. This factors as s plus 1 times s plus 2. And so we're going to rewrite accordingly. So we get 7s minus 1 over s minus 3, s plus 1, s plus 2. So turning to the third page now, you see that's exactly what we should have here. And the partial fraction decomposition, well, it goes by factors, right? So these are all linear factors, meaning degree 1. So on the top you get 1 degree lower, i.e. a constant. So you get a over s minus 3 plus b over s plus 1 plus c over s plus 2. And now we just need to find ultimately we need to find the numerator constants a, b, and c. But if you remember, before we can do that, we have to do a little bit of recombining here. So what we know is that a over s minus 3 plus b over s plus 1 plus c over s plus 2 equals, well, the common denominator is, you guessed it, s minus 3, s plus 1, s plus 2. And so you'll notice the a already has an s minus 3, so it needs the other two factors. I encourage you to work this out if you already know what to do. Okay. And now, well, this whole fraction here, this has to equal the left-hand side, right? Like this has to equal 7s minus 1 all over s minus 3 times s plus 1 times s plus 2. Well, so what that tells us is the following equation here, that the numerators must be the same. All right, well, in the next video, we'll pick up there as we solve for a, b, and c.